In an earlier video, we learned about the idea of a z-score. We learned that a z-score is a measure of position. It tells you where a data value stands compared to the mean. We learned that a data value that's below the mean or below average will have a negative z-score, and a data value that's above the mean or above average will have a positive z-score. Also, we learned that a data value that's further from the mean or further from average will have a bigger z-score. In other words, a data value that's more extreme will have a bigger z-score. In this video, we'll learn about two new types of z-scores. The first one that we'll learn about is called the z-score of a sample mean, which is basically just a z-score for a sample mean. It's a data value that shows, it's a value that shows the number of standard errors that a sample mean falls below or above a population mean. I think this definition will make a little bit more sense if we look at the concept in a diagram. In this diagram, we're imagining that a certain population has a mean age of 25 years and a standard deviation of 8 years. Also, we're imagining that a random sample of 16 people is being selected from the population, that the ages of the 16 people are being recorded, and that the mean age of the 16 people is being calculated. In this situation, the sample mean will come out to a certain number. The number that it comes out to depends on which 16 people happen to be selected. The sample mean could come out to any number along this number line. It might come out to 27, it might come out to 21, or it might come out to 19. It just depends on which 16 people happen to be selected. Underneath this number line, I marked off some z-scores. I'll explain where these z-scores came from. Before we understand where these z-scores came from, we have to look at this formula, which is the standard error. When a sample mean is being calculated, the standard error is the population standard deviation, sigma, divided by the square root of the sample size n. In this situation, those two numbers are 8 and 16. So the standard error is just 8 divided by the square root of 16. The square root of 16 is 4, so 8 divided by 4 is 2, and 2 is the standard error. Since the standard error is 2, that means that in this situation, we would expect the sample mean to be about 2 from the population mean. That's the amount of error that would be typical in this situation. In this situation, we would expect the sample mean to be somewhere between 23 and 27, because that's 2 in either direction of the population mean. Now let's talk about how the standard error fits in with this idea of a z-score. First, we need to realize that the population mean, which is 25, has a z-score of 0. And then if we go up by one standard error, which is 2, we get to our first z-score. This first z-score of +1 is one standard error above the population mean. If you start at the population mean and jump up one standard error of 2, you get to this first z-score. If you jump up one more standard error and go up by 2 again, you get to 29, which has a z-score of 2. And if you go up one more standard error and go up to 31, you get to the z-score of +3. If you start at the population mean of 25, which has a z-score of 0, and you go down one standard error, which in this case is going down by 2, you get to -1. If you go down one standard error again by 2, you get to -2. And if you go down one more standard error, you get to -3. So overall, the mean of the population always has a z-score of 0. That's always the way how it is. And if you go up one standard error, you get to +1. If you go down one standard error, you get to -1. If you go up 2 standard errors, you get to +2. And if you go down 2 standard errors to the left, you get to -2. So the z-score is really just a multiple of the standard error. In other words, it's just one jump of the standard error at a time in either direction. So if in this situation, if the sample mean comes out to 19, then the sample mean has a z-score of -3, because in that case the sample mean is 3 standard errors below the population mean. If the sample mean comes out to 31, then the sample mean has a z-score of +3, because in that case the sample mean is 3 standard errors above the population mean. Or if the sample mean comes out to 29, then the sample mean has a z-score of +2 because the sample mean is 2 standard errors above the population mean. So now that we've looked at this concept in a diagram, let's look at the actual formula for the z-score of a sample mean. The z-score of a sample mean can be calculated with this formula. You take the sample mean, x bar, subtract it by the population mean, mu, and divide by the standard error. When you use this formula, you turn the sample mean into a z-score, and that z-score tells you whether the sample mean is below or above the population mean, and also how far the sample mean is from the population mean, or how extreme the sample mean is. Here's our first example of using this formula to calculate the z-score of a sample mean. In this situation, we're imagining that a certain population has a mean age of 25 years and a standard deviation of 4.9 years. We're also imagining that a certain person randomly selects 18 people from the population, records their ages, and calculates the mean age of the sample to estimate the population mean. In this situation, this person doesn't know that the population mean is 25, but this person is trying to estimate that number, and the number that the person ended up calculating with his or her sample was 24.5. We can turn this sample mean into a z-score. So we take 24.5, plug it in here, take the population mean of 25, plug it in here. So this is just the mean age of the sample and the mean age of the population. We take the population standard deviation 4.9 and plug it in here, and the sample size, which is 18, and plug it in here. Next, we find the square root of 18, which is 4.24. We divide on the bottom 4.9 divided by 4.24, which is 1.16. We subtract the two numbers on the top to get an answer. And then once we get that answer, which is -0.5, we just divide -0.5 divided by 1.16, and we get -0.43. That number is the z-score of our sample mean of 24.5. Our sample mean of 24.5 has a z-score of -0.43. The z-score is negative, which means that our sample mean is below the population mean. We can see that that's true if we look up here. 24.5 is definitely below 25. Let's now look at a diagram to help us get an idea of what the z-score is telling us. First, let's answer this question. This z-score is telling us that the sample mean, which is 24.5, is 0.43 standard errors below the population mean, which is 25. And I think that statement will make more sense once we see this diagram. So this is the sample mean, which is 24.5. I just wrote an x bar for the sample mean. 0, the z-score of 0 right here, is the population mean of 25. And this is just showing us that this sample mean is a little bit below the population mean. It's not far enough below the population mean to be at the z-score of -1, but it's far enough below the population mean to be about halfway to -1. So like I said, here's 25, the population mean. Here's a sample mean 24.5, and it's a little bit below the population mean. It's 0.43 standard errors, or about half a standard error below the population mean. So it's not a very extreme sample mean. It's pretty close to the population mean. Let's now talk about the z-score of a sample proportion. This is basically just a third z-score that's now being applied to a sample proportion to tell us how extreme a sample proportion is. The z-score of a sample proportion is a value that shows the number of standard errors that a sample proportion falls below or above a population proportion. And it has its own formula. The sample proportion is p hat. In an earlier video, I said that a sample proportion is just a sample percentage written as a decimal. So if a sample of people is 45% male, then the sample proportion p hat would be 0.45 because the sample is 0.45 male. The symbol for population proportion is p. So if that sample that's 45% male came from a population that's 50% male, the population proportion p would be 0.50. Here's p again, population proportion, or population percentage as a decimal. Here's p again, and here's n, which is the sample size. Let's go through an example of using this formula. We'll take a sample proportion and turn it into a z-score. In this example, a population is 45% male, and a person randomly selects 28 people from this population, records their ages, and calculates the proportion or percentage of males in the sample. The sample that was selected turns out to be 52% male. So the entire population that the sample came from is 45% male, and the 28 people in the sample are 52% male. In other words, this sample of 28 people is about half male. It's maybe 15 males and 13 females. So let's plug these numbers in. Here we have the sample portion, which is 45%. That's 0.45 if we make it into a decimal. So 0.45 is p hat. P, which is the population proportion, is I'm sorry, I didn't say this correctly. Let me go back a little bit. The sample is 52% male, which means that the sample proportion is 0.52. That's p hat. The population is 45% male, so p is 0.45. Let's plug those two numbers in up here. Once again, p is 0.45 and p is 0.45 right here. The sample size, which is 28, goes right here. So proportion of males in the sample, proportion of males in the population, proportion of males in the population, and again right here, proportion of males in the population, and sample size. This comes out to 0.78. So our sample proportion of 0.52 has a z-score of 0.78. It makes sense that it's a positive number because the sample proportion is above the population proportion. And this z-score is just telling us that the sample proportion is 0.78 standard errors above the population proportion. Remember, I told you that the z-score of a sample mean is the number of standard errors that the sample mean differs from the population mean. And the sample proportion right here is just the number of standard errors. The sample proportion differs from the population proportion. It's the same concept. Let's look at this in the diagram. This sample proportion, which is 0.52, is right here, the p hat. The population proportion is 0.45. That's right here at 0, because the population statistic is always at 0. And this is just telling us that our sample proportion is a little bit above the population proportion. It's not far enough to be at +1, but it's about halfway there. Like I said, it's 0.78, or about 3/4 of a standard error above the population proportion. So overall, the z-score of a sample mean tells you how extreme a sample mean is. It tells you how far a sample mean is from the population mean in terms of standard errors. And A z-score of a sample proportion tells you how extreme a sample proportion is, or how far a sample proportion is away from a population proportion. And it's once again in terms of standard errors.